Back to calculus 3. This time we are moving to chain rule. Chain rule involving with partial derivatives. Partial derivatives. How about let's just jump into this example first. It's checkpoint 4.23 from the textbook. Let's take a quick look what this thing is about. Z is a function of two variables, and x also it is a function of t, and y is a function of t. So I'm saying eventually this function z can be considered as a function of t. And if you ask for the reason, I would say consider t as time. Okay, x and y are the coordinates, are the locations. Okay, each depends on the time t, and then the function value depends on location. So eventually you can say the function depends on the time t here. Okay, and what we need to consider here is to find out dz dt, the derivative z with respect to t. It's a regular derivative. It's a regular derivative. Certainly, one way to handle the situation, you could plug in, okay, this part for x and the other for y directly. But anyway, as you can tell, it's kind of getting a little longer. Eventually, we'll still get it. Okay, in this case, it's not a big deal at all. But anyway, I just want to illustrate the idea. How do you calculate this derivative, regular derivative, using the chain rule involving with partial derivatives? So think very carefully. This z, eventually it is a function of time t. But anyway, t is causing changing of this z in two ways. This t will cause change in x first, and then accordingly the function will change according to x. Also, t is causing changing in y, and that part of change also will change the function value. So what we need to consider here is this derivative dz dt. It is calculated in two ways because it is affected in two ways. The rate of change with respect to x, and then dx dt. And look at this part only. I would say it looks like a regular chain rule, but you want to be a little more sensitive. Remember, this is the Greek letter delta. It's the partial derivative notation. That is a regular derivative. Okay, roughly you can say that will generate dz dt because dx is cancelled. But anyway, that part only reflects the change of t in the direction of x. Okay, so we also need to consider change of t in the direction of y. So that part, it is arranged in a similar fashion. dz dy, then dy dt. And this is really what this formula is about. And how about let's take a look the calculation, how the calculation would work out. dz dt, so first we need to calculate dz dx, partial derivative with respect to x. So that would be 2x minus, actually I think I missed the part here. It should be 2x minus 3y because that's from 3xy. Then 2y squared is gone. Okay. Then dx dt, because x is given as 3 times sine t, so sine 2t, so dx dt, it is 3 still there, and the chain rule for the sine part, so it comes out another 2. Sine tends to be cosine. 3 times 2 times cosine 2t. This is just for this part. This term here, it is for those two derivatives. Okay, and then we consider change of t in the direction y, dz dy, still from here. So that's a negative 3x plus 4y. dy dt, it is 4 derivative cosine, that's a negative 2 times sine 2t. Still the chain rule involved. And mostly for this part, I'm just going to explain the idea. I hope it makes sense. And if you are watching the video, you may want to pause to take a look if this arrangement makes sense to you. Because the next case we are considering, really, it is based on this arrangement. Okay, certainly this example it is not finished, but anyway, I say the chain rule part it is done. So I'm going to leave the remaining part for you to finish. All right, this is the chain rule for one independent variable. And also, we are going to cover another case, chain rule for two independent variables. And what we are having here is if we are having the case like z is a function of x and y, then x is a function of u and v. At the same time, y is a function of u and v. I hope you can see, eventually we can consider z as a function of u and v. So I'm saying those two notations make sense to you, right? This is the partial derivative of z with respect to u, partial derivative of z with respect to v. But keep in mind, dz du, this u is causing change of z in two ways, in the x direction and in the y direction. So if you think very carefully, this formula really, it is derived, same arrangement like we did a moment ago. But this time, we are having all partial derivatives. Z is a function of two variables, so they are all partial derivatives. X is a function of two variables, they are all partial derivatives. dz du, all from partial derivatives. And also, if you recognize this is the partial derivative, so we are having another partial derivative, dz dv. It is arranged in a similar fashion. V is causing changing in the x direction and the y direction, so there are two terms. How about let's look at this example. This example might be pretty big. And when I was typing this problem, I was thinking maybe I change a different one. But anyway, I just decide to keep this as it is. Okay. It is checkpoint 4.24. It is not too complicated if you do understand the arrangement of the chain rule from the partial derivatives. So z is a function like such, and then x is a function of u and v. Y is also a function of u and v in a similar fashion. And then we calculate dz du. I just copied on the formula. Still keep in mind, u is causing change in the x direction and in the y direction. So dz du should be counted with those two parts, should count those two parts. Okay. And then dz dx, you take a look at the function here. This is the part I just want to explain. You do need to use the quotient rule, the derivative quotient rule with respect to x. This is what I got. And then dx du, it is from here. Okay, this is the exponential function. Cosine 3v is a constant. So I'm just having this 2 times e to the 2u cosine 3v. The first term. And the second term, it is dz dy. So from here, actually, you're going to use the quotient rule again. But this time, it is with respect to y. So this is what I got. And then dy du. dy du. So again, it is 2 times e to 2u sine 3v stays as it is. And still, it does take a little effort to simplify or combining like terms. I think I did it. And also, you want to double check if I'm getting all those numbers correctly. I hope I did, but anyway, you really want to double check, okay? And also I want to say, make sure you do understand how the arrangement of the chain rule works. Arrangement of chain rule works. It's from this part of the line, immediately after this general arrangement, okay? And then if you understand this part very well, hopefully you figure out we can do the same thing for dz dv. So the next page, I have dz dv. Okay, eventually z is a function of u and v, but v is coding changing in the x direction and y direction, so it's getting those two times. And the dz dx, really this part, it is the same as we just calculated previously. And the dz dy here, still it's the same as we calculated from here. I just copy and pasted mostly. And then you need to calculate dx dv and dy dv. X is given as such, y is given as such. So as I'm saying, if I simply move screen around and then keep on talking, I guess it might not be very helpful. As you can tell, the situation is quite complicated. So I'm not going to talk a lot for now. I want to read the notes and then give a try if you can rewrite, or really if you could get those partial derivatives by yourself and then do some necessary simplification. It would be a lot easier. So that is the material of section 4.5, chain rule involving with partial derivatives. We worked on two cases, chain rule for one independent variable and then chain rule for two independent variables. Okay, there are two layers of variables. Z is given as a function of x and y, then x and y are both some other functions. Or both are some other functions. So there are chain rules involved. Okay. Section 4.5. Thank you for watching.